In this last video, we're going to look at two optimization problems in preparation for our Calculus 1 final exam. If you recall, for every optimization problem, we should identify our objective function, our constraint functions, use the constraint function to rewrite our objective, apply some derivative work, and then answer the question. So we have this enclosure. This is a top-down view of some sort of enclosure or barnyard that needs to be constructed. The fence on the exterior costs $5 per meter, but the cost of the fence for the interior dividers is $20 per meter. Our objective is to find the dimensions x and y that minimize the cost of the enclosure. So let's just look at this for a second here. The cost is equal to $5. Well, maybe we can look at it a different way here. Let me say it this way. The cost is equal to the perimeter fencing plus the cost of the interior fencing. You know, that's what our total cost is going to be. And so as far as our constraints go, the perimeter fencing is $5 times what it looks to be 1y here and here, so that's 2y, and then we've got x on the top and x on the bottom, so plus 2x. Now that may or may not be easier to calculate in the future by saying 10 times x plus y. Now our interior, on the other hand, and I'll use a different color here, I think, has one x value, so this whole length is x, and then we've got two y values, and the perimeter, the interior costs $20 per meter, and that's going to be 1x plus 2y. And so when we write our cost function, we have 10 times x plus y plus 20 times x plus 2y. And, that might be nice to, distribute actually. I thought maybe factoring this would be good, but we'll have 10x plus 10y plus 20x plus 40y. And I'm starting to think that by combining these like terms, 10x and 20x, to be 30x, and these like terms, 10y and 40y, we might have a simpler constraint function to work with. Objective function to work with. And now we've got 50y. But we still can't really solve this because I've got two variables involved. And that's where our last component of the constraint comes into play. And some would argue that these first equations that I wrote, perimeter and interior, may not have been part of the constraint function at all. And I can understand that. But our restriction here is that the area has to have a total area of 60 square meters. So evidently 60 must be equal to x times y, and therefore say x by itself or y by itself could be identified. And I'll just say that y is equal to 60 divided by x. This is the key that's going to allow us to rewrite our objective function in terms of the constraints, and then ultimately, find the correct answer. So now we're saying that our cost is equal to 30x plus 50 times 60 over x. Or in other words, our cost is 30x plus 300 over x. And we can compute the derivative of our cost function now. And set the derivative equal to 0, because when the derivative equals 0, we can locate either a maximum or a minimum point of the function. And it looks like our minimum cost function, or minimum cost, is going to exist when x is equal to positive or negative 10. Now, of course, we can't have an x length of the negative square root of 10, so I'm thinking that the minimum is going to occur when x is equal to the square root of 10. We should confirm that, however, by considering the second derivative. So c double prime, and that's equal to 0 plus 600 over x cubed. So the signs change, and we're multiplying this denominator degree by the numerator value. And I can see that if I substitute the square root of 10 into x at this point, I'll end up with a positive c double prime. And when c double prime is positive, that means the graph is concave up. And if we're at a position where the graph is concave up while the derivative is equal to 0, then I know that we've encountered a minimum point. So that's a good double check here. So it appears that the dimensions necessary to minimize the cost is going to be when x is equal to the square root of 10, and y then would have to be equal to 60 divided by the square root of 10. And both of those are measured in meters. And by the way, we could investigate this solution if time permits, and we can substitute these two numbers into the cost function and then pick other values that may work. For example, the pen, since its area is equal to 60, could have dimensions of 6 and 10, right? 6 times 10. Or perhaps, something crazy like 60 and 1 unit, etc. So we could pick a lot of different x and y values to investigate the cost. And if it anecdotally appears that these are the minimum values, then I think we've done a pretty good job. So I would consider that if you have spare time on the test and you want to confirm your result. And now to finish out this series of examples, let's find the coordinates of the point in the first quadrant. So with positive and x and y values, that is the closest to the origin. So in this case, we've got to remember that the distance formula is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. And as it turns out, since our origin has an x and y value of 0, 0, we could say that this is the distance formula, x squared plus y squared. And then this would be our objective. And our objective is to minimize this distance function. And what we're limited to, or what we're constrained by, is that the y coordinate has to be equal to 9/2 minus x squared. So if we use this notion to substitute y in this case, we now have a derivative, a distance that's equal to the square root of x squared plus 9/2 minus x squared, quantity squared. And we can compute the derivative of this, and, well, we should probably simplify first and then compute the derivative and find the minimum distance. I am going to use a trick that we employed in class, and I'm going to square both sides of the equation to say that d squared is equal to x squared plus, and 9/2 minus x squared, when we FOIL that together, 9/2 squared is 81/4. We get 2 of the outside and inside products, so that's going to be 18/2, or 9x squared, and then plus x to the 4th. So if we were to write this in standard form, we'll see that d squared is x to the 4th minus 8x squared plus 81/4. To minimize this function, we would take the derivative of both sides. In this case, with respect to x would be just fine, so d dx. And that leaves us with 2d d dx equals 4x cubed minus 16x plus 0. And since we want the distance to be at a minimum, or the rate of change to be 0 at that particular moment, we'll set that equal to 0, and we now have the expression 0 equals 4x cubed minus 16x. So it looks like we're going to have a minimum point. Let's see here. Let's set this thing equal to 0 by factoring first. 0 equals common factor of 4 and x. Let's call that x squared minus 4. So I think when x is equal to 0, when x is equal to 2, and when x is equal to negative 2, we'll be at a minimum. We're going to throw out negative 2, of course, because that's not in the first quadrant. We're going to throw out 0 because that's not in the first quadrant either. That's right on the axis. So it looks like when x is 2, that will generate a coordinate that's got a minimum distance to the origin. And when x is 2, we could say that let's find our y coordinate first. Y is equal to 9/2 minus 2 squared. So 9/2 minus 4. That's 4.5 minus 4. So that leaves us with a y value of 1/2. So we're thinking at the coordinate 2, 1/2, which, I don't know, this graph might be drawn pretty accurately here. At this position, the distance is at a minimum. So the distance at this particular location is equal to the square root of 2 squared plus 1/2 squared. And I'm using a calculator off screen to do this. I see that distance is approximately it's precisely, when simplified, the square root of 17 over 2. Or, in other words, the square root of the fraction 17/4. And I think it'd be worthwhile to calculate this distance just to, again, anecdotally confirm that we did find a minimum. And we didn't have any other coordinates to investigate. And it does seem appropriate based on the sketch that we have here that at some point here, perhaps, that the diagonal distance is at a minimum. Clearly, if we measured from the origin to, say, this position, that distance is much greater. And then even at this point, from this position to here, that's probably longer than the diagonal distance that we just computed. And so to confirm that, we can, of course, use the second derivative test. We could use a first derivative test, which I think may be easier in this case. Or, in the interest of time, we can discuss it anecdotally and compute some other distances with other coordinates that are known in that vicinity. But I think I'll leave that for you to ponder and think about and perhaps practice on your own. If you've got any further questions with regards to this review, by all means, send me some messages through either email or Schoology, and I'd be happy to address them as they come in. Thanks for watching.